So you can see that there's LEDs there and right there. So I'm going to show you from far as I go up the frequency sweep. And one is turning on. Wait, is that one turning on? Oh, there we go. There we go. And this one's also on. Okay, so basically, I actually didn't see what frequency I stopped at. Okay, 352. I've done this a long time ago actually, so, and I realized that, like, I used my oscilloscope there, and I found out that 3.85 was at its strongest, so I'm just gonna slowly move that up to 3.85. And oh, too far. Okay. Alright, and yeah, I've messed around with these coils a lot before, so it's kind of not in good condition compared to what it used to be. Okay, so here's the brightness of one LED of the transmitter, and here is the brightness of transmitter 2. Okay, I'm going to show you. Okay, no. Before I show you the different properties, I'm going to explain what the claims say and what I think is actually going on. So the claims say that there are longitudinal scalar waves coming out of this and traveling to there, and that the distance does not matter as long as there's this wire, the ground wire, the single wire transmission. And I'll show you. It's just one wire. There's no two wires here. Alright, and so yeah, they say that there's longitudinal scalar waves that's not affected by how far this ball goes. And to prove that the distance doesn't really matter, I'll slide it and you can see that there's still, oh, it did turn off. What? Okay, no, there we go. Well, here's the thing. When it has some sort of interference when you touch it, and when you get really close to it, but not like electromagnetic waves. And that's what I want to show you, and that's what I want to ask. So you can see the distance right here. You know, this is being powered by this thing right here, Syscon. Like it's not that powerful. So electromagnetic field cannot power those LEDs with this power supply at this range. And you know, I don't think this setup is even strong enough. Like this spiral coil, I chose spiral coil because it was according to the plans of Steve Jackson, what I replicated from. And apparently spiral coil, it cancels out the magnetic field, but later on I realized it doesn't fully cancel it out. It just has a weaker magnetic field. And basically what's happening is there's a current going through the white wire, and it induces a current in this one. And the claims are that there's no current here. There's just high voltage and either close to zero or zero current. But that doesn't make sense to me, because at this part you're getting your voltage, you're getting your lights turned on through the white wire, which is not connected to the blue wire. So if there's no voltage, if there's no current and only voltage, then how is there induction into this white wire? You need a current in order to have a magnetic field. You need moving electrons, right? So I don't think that scalar waves, the claim is that they're produced through voltage with no current. And yeah, there's definitely currents here. And I mean, if you can explain me how there's no current and how there's some sort of induction, at least in that one, then you know, maybe then I'll believe you. But there's some other problems. So like, I know it's not electromagnetic waves, but I also know it's not scalar waves for a different reason, and I'll explain that after. But just to show you that it's not electromagnetic, if you were to move this, this is a metal plate, by the way. You can see it's metal. Yeah, so here. Okay, it's metal. You know what, just to prove it to you, I know there's gonna be skeptics. Just to prove it to you, this is yeah, this is conductivity test or continuity test. Alright, let me first. Alright, so it makes a beep when I touch them. So I'm gonna have this one touching here. What? Wait. Okay, there we go. There, you can see that, right? I'm just pushing down on it. Okay, so I'm running out of filming time. Okay, so when I move this in front, it should get weaker, but it doesn't. However, when I do get close, like very close, wait, it does start to turn off, and especially when I touch it too. And here's the weird thing about it as well. When I move my hand, right, wait. When I move my hand, it starts to dim as well. Wait, or especially when I touch it. But even if I don't touch it, if I like, I'll get pretty close. Wait, maybe like usually from up top. Wait. Okay, see it. Oh, wait, see, look, it dimmed. I'm still not touching it. Still not touching it. Okay, so from that, I don't know, it's weird. And to also prove again that it's not electromagnetic, here's another metal plate here. I'm putting both of them. If it was electromagnetic, it would actually strengthen if you put it behind, right? Because it's just like flashing a light bulb at a mirror, right? It would reflect. So here I'm putting it behind, and the light is not dimming. I'm going to lift it up, right? I've lifted it up. Now I'm putting it back down behind it. You know, it's not dimming or brightening. When I put it in front, you know, it should dim at least a little, but it doesn't. And here, when I put this in front here, same stuff, right? But when I get close, alright, here we go. This one's kind of weird, I guess, because the input is directly connected. When I touch it, it doesn't really turn off. It kind of brightens when I touch it, which is weird. I don't know. Anyway, in here, when I touch it, it doesn't turn off either. But that one turns off when I touch it. So that's interesting. What I think is going on. Okay, so basically, I'm not going to use math, or I'm just going to use basic physics principles or chemistry. So there's a current being induced in this one. I'm running out of time. Sorry if I'm going a little fast. But there's a current being induced in this one, and this metal sphere is since it's aluminum, and since it's metal, it has empty shells. Sorry. Yeah, its electron shells are not full. It has empty spots. So electrons have space to go here, and it's AC, right? So it's traveling back and forth. So electrons are building up on here, and then leaving, going through this wire, coming into this one, and then building up in this sphere, and leaving that sphere empty. And when it travels back, since it's AC, it leaves this one empty, and all the electrons travel back to this one. So basically, it's going back and forth like that, kind of like Lenz's law. How you have the loop and the magnet. Magnet goes in and it pushes the electrons in one direction. When the magnet comes out, it pushes it in the opposite direction. There's no positive and negative for that. It's just Lenz's law. You know, you're moving the magnet back and forth, and it's moving the electrons. So that's what I think is happening here. The bigger the sphere, the better it works. Like that's a claim that I haven't really tested. But here, look, when I take this sphere out, interestingly enough, it turns off. And here's also what's interesting. I'll touch it and I'll turn on for a second, or I'll get really close. Look, I'm not even touching it, and hold on. See, I'm not even touching it, and it's lighting up. But if I move my hand away, it'll turn off. I don't know how that works exactly. But if I touch it, it turns off. I don't know. Okay, so I don't even know if my theory is correct, because I don't understand what happens when you get close to it. I'm just gonna connect that back. Okay, actually, let me show you. Yeah, inside is just it's just this right here. Styrofoam. Nothing in there. Just for you skeptics out there. Alright. And I'll be making a second video to show that it's not scalar waves, because I'll show you. It has to do with the ground. Alright, see you for now.